Hello everybody and welcome back to Elementary Statistics Online at Frederick Community College. In this video, I will talk to you about the central limit theorem and how to use your calculator to solve problems for this chapter. So this slide right here briefly tells us the main information from the central limit theorem. And basically what it says is that if we take a simple random sample of a large enough size, so that's greater than 30, from a population with parameters mu and standard deviation sigma, then regardless of the shape of the population, the distribution of the sampling mean will be approximately normal, and the mean of the sampling mean is the same as the mean of the population, and the standard deviation is found by taking the standard deviation of the population and dividing it by square root of n. Okay, so that is just a very quick review of what the main point of this theorem is. All right, so now let's go ahead and take a look at some problems. I'm going to go to chapter 7, problems with the mean for central limit theorem, and I'm going to do problem 2 and 5. So you might have slightly different numbers, slightly different scenarios, but the main ideas will be the same. So let's take a look at what we have here. The average number of miles in thousands that a car's tire will function before needing replacement is 65, and we have the standard deviation of 14. Suppose we take 11 randomly selected tires, and we want to answer all of these questions, assuming that the population is normally distributed. So what is the distribution of x? Okay, x represents the average number of miles that a car's tire will function before it needs to be replaced. So that is 65, and the standard deviation is 14. Okay. All right, what is the next question? The next question is, what is the distribution of x bar? Now this is x bar, which means it's not the same thing, right? This is sampling mean, okay? Now, the central limit theorem says that if we have a population that's normal, then the sample size does not need to be 30, okay, or bigger. So we do have the normal distribution. This line right here says that we have a population that's normally distributed. So we can do the central limit theorem. It says 65, the mean is the same. The population standard deviation divided by the square root of n, right? That's what we're going to do here. So let's go to 14 and divide by the square root of 11. Okay, that's going to be our standard deviation, 4.2212. Let me check. 4.2212. That's good. All right, let's answer the next 3 questions. If a randomly selected individual tire is tested, find the probability that the number of miles in thousands before it will need replacement is between 67.7 and 69.8. Okay, one tire. So we're going to go to second variables, and we choose in command 2 normal CDF, and the syntax for calculator is lower limit followed by upper limit, mean, and standard deviation. So the lower limit is 67.7, upper limit 69.8. What is the mean? The mean is 65. What is the standard deviation? Now this is for just one tire. Think about it as a very small sample of 1. So that would be 14. That is the standard deviation here. Okay? Close it. And we get this answer here. So 0.0577. Now, let's see what this question is asking us. for the 11 tire tested, right? So tires that are tested, 11 of them, find the probability that the average miles fall in the same range, right? So we have exactly the same range as above. So it might seem like it's asking us the same question, but it's not. Now we ask about the average mileage, okay? So what I'm going to do the following. I'm going to do second enter, and it's going to bring up the line that was used before, right above, right? So the reason why I'm doing it, because I really don't need to change much here. I just need to change this to 14 divided by the square root of 11. Okay, that is my standard deviation because I have a sample of 11 tires. Let's see what we get here. We get 0.1335. All right, now what about this part right here? For part D, is the assumption that distribution is normal necessary? The answer in this case is yes, definitely, because our sample is not that big, okay? If the sample was bigger than 30, then this assumption would not be necessary. But because it's a small sample, we need to make sure the underlying distribution is also normal. All right, let's see. Looking good, all green. That means we got it all correct. Okay, so that is a typical problem for central limit theorem topic, okay? Now, there's a couple of problems in this assignment that you need to know just one little rule, and I'm going to go ahead and go through this example. And on the test or on weekly assignments, I will not ask you to know this. But I think this is a fun topic, and it's something that you might be able to relate to further in your studies. So it's not a bad idea to take a look at this example. Okay, let's take a look at this problem. The average runtime for 5K is 21 minutes with a standard deviation of 2.5. 21 minutes, that's pretty fast actually. Around 5K is a lot. And then we have 49 runners that are randomly selected. Round all of your answers to 4 decimal places and where possible, and assume a normal distribution. Okay, so what do we have here? We have a normal distribution for the run-in time. 21 minutes is the average. Standard deviation is 2.5. Okay, that is just the distribution of the average time, okay, for all runners that run 5K. Let's take a look at the next line. What is the distribution of X bar? Okay, X bar, that is the sample mean, right? So the distribution is normal by the central limit theorem. So our first parameter is the same, 21 minutes, and now we have 49 runners. So for the sample, or for the standard deviation, we would do what? Let me clear all of this. So 2.5 divided by the square root of 49, which is 7, right? Okay. So we get 0.3571. That's what's going to go in here. 0.3571. Let's check this. Great. Now, this part right here, this one you might be asking me questions about because I asked you guys to skip this section. And yes, I did. But we can do 1 or 2 problems. And if you want to take a look at the reference in the textbook, then this is page 409. And all you need to know is this part right here. So if we were to solve these problems for the sum, the mean of the sum, then all we gotta do is multiply the mean by the sample size and the standard deviation by the square root of n. That's it. That's all you gotta do. So let's go ahead and go back and we'll solve the rest of these problems. Okay, so what is this one here? Okay, this is the distribution of the summation of x, right? So what do we have? The sample size is 49. So 49 times the mean would do 49 times the mean, which is 21, That's going to be 1,029, right? Okay, 1,029. All right. What about the standard deviation? So that would be the standard deviation times the square root of n, which is 7. So 7 times 2.5. 17.5. Okay. And now we have these questions to answer. If one randomly selected runner is timed, find the probability that this runner's time will be between 20.7643, 21.2643. Okay. I'm going to go back to my calculator. Second variables. Normal CDF 20.7643, 21.2643. Okay, and the mean is 21. The standard deviation is 2.5. All right, so I got 0.0797, right? 0.0797. 0797. Okay, good. So the next question. Now we have 49 runners. Find the probability of the average time falling into the same range, right? So I'm going to go back to my calculator and do this trick as I've done before. Second, enter. And here I need to change what? I need to change this to divide by the square root of 49, which is, I'm just going to type in 7. Okay, and my probability will be different because now my standard deviation is a lot smaller, which makes the probability higher. Okay, so 0.5157. All right, let's see what's going on here. Find the probability that the randomly selected 49% team will have a total time less than 1,033.9, right? So this is your hint, total time. The whole team has its total time less than this amount right here. So I'm going to be using this distribution, okay? With this is my mean and that's my standard deviation. So I'm going to go to second variables, CDF, okay? What is the lower limit? Less than. So I'm going to just take a large in absolute value negative number. And I know the book is teaching you to do 1E99. That's fine. You can do that. But for me, it's just easier to type in something like that. Any large in absolute value, but small in general, right? Number that's small because it's negative. That's going to be your low limit if you're doing a problem that says less than. Okay, so that's the low limit. Upper limit is 1,033.9. Mean is 1,029. And the standard deviation is 17.5, right? Now, I'm looking at this and I already know that I'm going to get higher than 50% chance of this happening. Why is that? Because if this is my mean, that sits right in the middle, right? And this is just to the right of this number. So I know I should get greater than 50% chance. Okay, so 61.3%, so 0.6103. Okay. All right. 0.6103. Where do you go? Here we go. Okay. That is my probability. Next question. For parts E and F, is the assumption of normal necessary? The answer here is no. Our sample size is large enough. We don't need to worry about normality for the population. Okay. So that's good. And the last question. The top 15% of all 49-person team relay races will compete in the championship round. Okay, so these are the 15% lowest times. What is the longest total time that is relating can have and still make it to the championship round. Okay, so we're not looking for while we're looking for the top 15, we're actually looking for the lowest scores, right? So these are the scores that are on the left side of the distribution. Okay, so if I need to find top or bottom percentages, I'm actually using inverse normal command. So I'm going to go to second variables, inverse normal. Okay, I need to find the smallest bottom 15%, right? So that's 0.15, even though they're the top as far as the time goes, right? Because the top for running is the shortest amount of time. You want to run as fast as possible. That's why for the distribution, in this case, the top scores are actually located on the bottom of the distribution. Okay, so 0.15, what is the mean? The mean is 1,029 because we're looking for the total time, and the standard deviation is 17.5. Okay, oops, keeps doing that. Here we go. All right, so the total time for a 49% team to make it to this championship should be 1,010.86 or smaller, right? Or less than that. So what do they want us to plug in? 4 decimal places. Okay, so 86.24. 10.8624. Let's see, is that right? Okay, that looks good. Okay, let's submit, see what we get. Everything looks great. Okay, so this type of problem, if you're worried that it's a little bit messy, right? Because it is. Don't worry about the tests. I'm not going to put anything like this in the test or even the weekly activities. But I think it's still a good idea for you guys to know that it's there. We can talk about the total average, and it's not really that much more complicated. All right, I hope this video was helpful. Thank you for watching.